Hi, this is Kwon and Jongmin from the Korea Advanced Institute of Science and Technology. We are the co-first authors of EcoSplat, Efficiency-controllable feed-forward 3D Gaussian splatting from multi-view images, and our advisors are Professor Ji-Hong Oh and Professor Munchro Kim. Novel view synthesis is a fundamental task in 3D vision, and although 3D GS has become a state-of-the-art approach, its per-scene optimization is time-consuming, motivating feed-forward methods that directly convert input images into pixel-aligned 3D Gaussians for efficient novel view rendering. Our goal is to enable explicit control over the number of 3D Gaussians for feed-forward GS, producing the best quality representation under a user-specified primitive budget while ensuring predictable memory, latency, and bandwidth. Our key contribution is an efficiency-controllable feed-forward 3D GS framework, where the number of output Gaussians exactly follows the user-defined budget at inference time, supported by a two-stage training scheme and achieving state-of-the-art performance over prior feed-forward methods. EcoSplat consists of two stages. First, PGT trains the model to predict dense pixel-aligned Gaussians, and then IGF fine-tunes the model with the target Gaussian budget as a conditioning signal to select the most important top K Gaussians for compact and high-quality rendering. In the first stage, PGT uses a shared vid encoder and multi-view decoder to aggregate information across input views, and then predicts pixel-aligned Gaussian attributes through separate center and parameter heads using a simple rendering loss. In the second stage, IGF freezes the geometry-related components and fine-tunes only the Gaussian parameter head, so that visibility and appearance are adapted to the target budget K while selecting the most important top K Gaussians for compact rendering. Here, we condition EcoSplat on the target budget by converting K into a preservation ratio, which allows the model to predict budget-aware opacities and assign higher importance to the most informative Gaussians. We further introduce an importance-aware opacity loss, which uses a pseudo-importance mask to encourage the model to suppress less important Gaussians while preserving the opacity of informative ones under the target budget. The importance mask generation for the importance-aware opacity loss consists of three steps: binary variation map generation, important Gaussians collection, and important Gaussians projection. First, we generate a binary variation map by combining photometric variation from the target image and geometric variation from the Gaussian normal map, then threshold it according to the preservation ratio. Second, we collect important Gaussians by keeping those located in high variation regions and also selecting representative Gaussians from low variation regions using K-means clustering. Third, we project the collected important Gaussians back to each input view to obtain the final importance mask for supervising the opacity prediction. EcoSplat consistently outperforms all baseline methods across different Gaussian budgets, showing that our explicit primitive control preserves high NVS quality even under very compact Gaussian settings. Across different input view settings, EcoSplat maintains competitive or superior rendering quality while using far fewer Gaussians, demonstrating that our method scales well with the number of input views. We show a qualitative comparison through a demo video to visually demonstrate the rendering quality of EcoSplat under controlled Gaussian budgets. In conclusion, EcoSplat enables explicit control over the number of Gaussians in feed-forward 3D GS, achieving flexible and efficient rendering across different device budgets while maintaining high-quality novel view synthesis. Thank you for your attention, and please visit the project page through the QR code for more details about EcoSplat.